I'm about to drop a completely original YouTube-style script inspired by the topic, built from scratch with heavy commentary and fresh framing. I'll treat this as a creator thinking out loud, not a recap, but a game of ideas sparked by Germany's Lake Laach hints of underground activity. Let's dive in. I'm going to start with a hook that rips off the band-aid. What if a sleeping volcano isn't really sleeping at all, but quietly stirring under our feet in a way we've never fully understood? What if thousands of microquakes aren't random noise, but a diary of what the Earth is trying to tell us about pressure, fluids, and hidden magma? Personally, I think that's the core tension here: a quiet surface, a restless interior, and scientists piecing together a map from whispers rather than shoutouts. Now, context up front. Lake Laach sits in a geologically complex area in Germany's Eifel region. For years, the surface looked calm, but more than 1,000 tiny earthquakes have revealed something deeper: a tilted underground reservoir connected to a broader fault network. In my view, the big takeaway isn't, is there magma, so much as, what does a tilted, pressure-fed system do to our understanding of dormant volcanic fields? This isn't just an academic drill, it changes how we monitor hazards, plan land use, and interpret quiet signals as meaningful disturbances. Let me break down the core ideas with my own spin, injecting interpretation, speculation, and the kind of nuance you'd hear from a thoughtful host on a late-night science show. Idea 1: a tilted reservoir changes how we read quakes. The scientists found a reservoir that isn't vertical but slanted toward a nearby basin. This geometry helps explain why quakes cluster on one side of the lake instead of circling it. What this really suggests, in my opinion, is that the underground architecture matters as much as the tremors themselves. If you tilt the plumbing, the water pressure doesn't spread evenly, it exerts sideways force on faults, nudging them to slip along preferred lines. Commentary and interpretation: this matters because fault movement isn't just about more pressure equals bigger quake. It's about the directionality of stress. In practice, a slanted reservoir could create asymmetric stress fields, producing bursts on one flank and quiet on the other. What people miss is how topology, the shape of the underground space, drives the narrative of seismic activity. If we map the tilt precisely, we can forecast not just where quakes happen, but which faults are most susceptible to slipping. This hints at a broader trend. As our sensors get denser and imaging improves, many suppose dormant zones may reveal preferred pathways shaped by ancient geometry rather than current magma surges alone. Why it matters and bigger trend: this challenges the simplistic view that a volcano's activity is a single vent story. Instead, we're looking at a field with many channels for fluids and pressures. The implication is a shift toward multi-vent hazard models, where early warning depends on tracking how fluid pressure redistributes in a broken crust. My takeaway: the crust isn't a static shell, it's a dynamic web where shape dictates rhythm. Idea 2: dense sensor networks rewrite the underground truth. The team deployed over 500 sensors and even used a 40-mile fiber optic line as a listening device. The level of resolution, down to 1 mile spacing in places, lets them see tiny structures that older surveys blurred. A year of data yielded 1,043 microearthquakes, mostly too small to feel, and patterns that look like repeated patches relaxing under pressure. Commentary and interpretation: this pursuit is a reminder that truth in geology often lives in the small signals, not the headline quakes. The high-density array acts like a medical MRI for the Earth, catching subtle movements and transient signals that hint at fluid flow and stress changes. What people don't realize is how fragile our older mental models are: a single big tremor used to define risk, while microquakes were treated as noise. Here, those noises become the main chorus. Why it matters and bigger trend: we're moving toward an era where continuous, high-granularity monitoring becomes standard for volcanic regions. If tiny tremors map out a hidden reservoir and its tilt, we can design more targeted monitoring around critical stress hotspots. It's a shift from periodic surveys to continuous listening, a paradigm that changes how we respond to unrest and allocate resources for evacuation planning and public communication. Idea 3: fluid movement and potential magmatic signals. Some seismic reflections suggest fluids released by melt are present between rock layers, possibly magma or magmatic fluids pooling in those layers. The researchers are careful to say this is not a definitive sign of imminent eruption. The uncertainty around whether those signals come from magma or from other hot fluids matters because the physics of a pressurized magma pocket behave differently from gas or water in cracks. Commentary and interpretation. This is the subtlety that makes planetary geology fascinating. Uncertainty isn't a failure, it's a feature. It forces us to ask tough questions about how to calibrate our risk models. If those fluids are magmatic, it raises the stakes for monitoring gas emissions, crustal deformation, and near-surface seismicity. If they aren't, the same signals could still teach us how fluids move through old volcanic plumbing without triggering an eruption. The broader trend here is methodological rigor, using multiple lines of evidence to triangulate the reality, and resisting the urge to leap to sensational conclusions. Why it matters and bigger trend. It emphasizes the need for multidisciplinary approaches, seismology, gas chemistry, and rock mechanics, to understand complex crustal systems. The public takeaway should be that presence of fluids does not equal impending eruption, but it does mean the system remains dynamically active, which has implications for hazard planning and regional preparedness. Idea 4: a long memory in the crust and new baselines for the Eiffel. Lake Laach last erupted over 13,000 years ago, yet the deeper signals hint at ongoing activity in the surrounding crust. The new map doesn't claim an eruption is imminent, but it establishes a sharper baseline. Unrest in the Eiffel should be judged against a high-resolution picture of what the crust is actually doing beneath the surface. Commentary and interpretation. The new baseline idea is powerful. It reframes how we think about dormancy. Dormant doesn't mean dormant forever, it means quiet enough that it's easy to miss what's brewing underground. If we treat this region as a connected system with an evolving backbone of stress and fluid pathways, then every tremor becomes data about a living crust rather than a one-off anomaly. What people misunderstand is the complacency of the word dormant. The crust remembers, and it occasionally whispers. Why it matters and bigger trend. The broader implication is a shift toward proactive monitoring in multi-vent volcanic fields, where the next eruption could follow unexpected routes rather than the last vent. The takeaway for policymakers and residents is that awareness doesn't require fear, but it does require robust, continuous observation and transparent communication about what the science actually says. Deeper insight. What this tells us about how we study quiet geologies. Reading the Laach region teaches a broader lesson. The quietest landscapes can hide deeply active underworlds. The combination of a tilted reservoir, a silken web of minor quakes, and signs of fluids points to a crust that is both older and more dynamic than traditional models assumed. We're seeing a pattern where interior processes leave subtle fingerprints on the surface, not dramatic eruptions, but meaningful shifts that shape hazard plans and public understanding. In my opinion, this aligns with a global trend. Scientists are increasingly embracing the complexity of crustal systems, using dense sensor grids, cross-disciplinary data, and nuanced interpretation to avoid oversimplified narratives. The takeaway isn't that we've found a ticking time bomb, it's that the Earth's crust is a layered, interconnected system where small signals accumulate into a real story about pressure, pathways, and potential reactivation. Closing thought. If you take a step back and think about it, the Laach findings challenge the narrative of dormant volcanoes as mere relics. They are active, in ways that aren't always explosive but are nonetheless meaningful for how we live with risk. The question I'm left with is, how many other quiet regions have similar hidden plumbing and what would a truly high-resolution map reveal about them? For viewers, the practical question is this: how ready are we to adapt our monitoring, our land use decisions, and our risk communications to a crust that is revealing more of its character, not less? If you found this line of thinking interesting, tell me in the comments. Do you want me to dive deeper into how dense seismic networks work in practice, or into how gas chemistry signals corroborate or contradict seismic clues? And would you prefer a deep dive episode focusing on the science methods, or a broader, implications-focused piece about living with dormant volcanic regions around the world?